Good morning, everyone. My name is Kyle Miller. I'm in the class of Control Systems, Technology Online. Today I'll be going over PI, and PID controllers. I'd like to start out by showing my outline. I'm going to have a separate slide for introduction to the control systems, P controller, I controller, D controller, PI controller, PID controller. I'll have a conclusion and I'll show all my references. Introduction to control systems. The purpose of control systems is to manage, regulate, and direct the behavior of other systems to achieve a desired output or performance. In engineering and industrial context, control systems automatically adjust process variables such as temperature, speed, pressure, or position to maintain them at a specific set point, even in the presence of external disturbances. This ensures stability, accuracy, and efficiency in machines and processes without requiring constant manual intervention. Now, control systems are essential in countless applications, from everyday household appliances like thermostats and washing machines to complex systems like aerospace, manufacturing, and robotics. By continuously monitoring outputs and comparing them with the desired input values, control systems generate correctiveness actions through controllers like the ones I'm going to be talking about all day to minimize error and optimize performance. Now, their ultimate goal is to create systems that are reliable, safe, and the ones that operate smoothly under a wide range of conditions. P controller, or proportional controller. It is the simplest type of feedback controller, which uses the regular systems by reducing the error between a desired set point and the actual output. It does this by producing an output that is directly proportional to the error. The controller signal is calculated using the formula shown in the PowerPoint there, where Kp is the proportional gain and Et is the error. This means that the larger the error, the stronger the corrective actions applied to the system. The main advantage of a P controller is that it's fast and straightforward response to changes in system conditions or disturbances. However, a P controller cannot eliminate the steady state of error, especially in systems where the output needs to be exactly at the set point. As the error decreases, the controller actions also decrease, which can leave the system slightly off target, while increasing the proportional gain can reduce this error. It may also cause a system to overshoot the target and become more unstable. So it's not going to hit the set point exactly. It's going to kind of range around it. Despite this limitation, P controllers are still effective in systems where a smaller error is acceptable, and they are often used in simple applications or as part of a more advanced controllers like PI or PID systems. I controller, or integral controller, is a type of controller system designed to eliminate steady-state error by considering the accumulative error over time. Unlike a proportional controller, which reacts only to the current error, an I controller looks at the history of the error and generates a control signal based on the total sum of past errors. The control action is defined by the equation shown on the board there, where UT is the control output and ET is the error, and KI is the integral gain. This means the longer an error persists, the stronger the corrective actions become, ensuring the system eventually reaches the desired set point. Now, the main advantage of an I controller is its ability to completely eliminate steady-state error, making it very useful in systems where high accuracy is required. However, because it reacts to the cumulative error rather than immediate changes, it tends to have a slower response time. It can also lead to an overshooting and oscillations if not properly tuned, especially in systems with fast dynamics. I controllers are often used in processes where small, very small, consent errors and errors need to be corrected over time, such as in levels of, say, controlling tanks or slow changing temperature systems. Now, on their own, they are rarely used, but they do play a very crucial role when combined with other proportional controls like PI or PID controllers. D controller, derivative controller. Its main purpose is to predict future error to dampen system response. How might that work? Here's the equation, shown above. It reacts to the rate of error change. The components are quite simple: gain KD and a differentiator. Applications: position control in robotics and missile guidance systems. Now, the D controller, in my opinion, is the most fascinating. To sum it up, it's a type of controller strategy that reacts to the actual rate of change of error signal rather than the magnitude of error itself. Its primary function literally predicts the system's future behavior by analyzing how quickly the error is changed over time. Mathematically, this is by far the best controller. The PI controller, also known as the proportional/integral controller. So the PI controller is designed to provide precision and stable control of dynamic systems by combining the strengths of proportional and integral control actions. Now, the primary purpose is to maintain a system's output at a desired set point by minimizing the error between the two set points and the actual process variable. The proportional P component reacts to the current error, delivering a control signal that is directly proportional to the size of the error. This offers immediate correction and helps the systems respond quickly and change the disturbances. However, a proportional controller alone often leaves a steady state error, where the system's output hovers near but never really reaches the set goal. This is where the integral I component becomes essential. Combine these two, and it pretty much gets the job done. The integral term sums the error over time and applies a correction based on the accumulative value. This effectively eliminates the steady state error by continuously adjusting the control output until the error is reduced to zero. Together, the components complement each other. Proportional control offers fast response, while integral control ensures long-term accuracy. The purpose of combining the two into a PI controller is to achieve both responsive and accuracy in a system without the complexity or noise sensitivity that a D component introduces. This makes the PI controller ideal for many practical control applications where noise is present or where the derivative term might cause instability. PI controllers are very simple. They're made simpler to implement and tune compared to full PID controllers, while still offering reliability, performance, and steady state in transient conditions. PI controllers are used widely in industries such as chemical processing, HVAC, motor speed regulations, and liquid level control, where precision and stability are more important. For example, in a temperature-controlled system, a PI controller can ensure the desired temperature is reached and maintained without excessive oscillations or delays. Overall, the PI controller provides a good balance between simplicity and performance, making it one of the most commonly used controllers in both industrial and embedded systems. PI controller, proportional/integral/derivative controller. Is a widely used controller strategy that combines all three of the key actions. Now, the goal of a PID controller is to provide a fast, accurate, and stable response by addressing the current error, past accumulative errors, and the predicted future trends of the error. Now, the control signal is calculated as that equation shown in the PowerPoint there, where Kp, Ki, and Kd are all gains for the proportional, integral, and derivative components, respectively. This combination allows the PID controllers to not only respond quickly to changes, but to also eliminate steady-state errors and reduce overshooting or oscillations by anticipating future errors. Now, the PID controller is valued for its versatility and reliability, making it suitable for a really wide range of industrial and commercial applications. It is commonly used in systems such as motor speed control, temperature regulations, pressure systems, robotics, and even in flight controls. Because it has addressed the limitations of P, PI, and PD controllers individually, a well-tuned PID controller offers a perfect balance performance in both transit, and steady state conditions. However, proper tuning of the three gains is crucial. Poor tuning can lead in instability or sluggish behavior. Despite this, PID controllers remain the standard solution in automotive and process controls due to their effectiveness, flexibility, and relatively simple implementations. In conclusion, controllers are the foundation of modern automated systems, providing the intelligence requires to keep processes running smoothly and within desired parameters. By continuously monitoring the difference between the actual output and the target set point, controllers apply calculated corrections to reduce or eliminate error. This feedback-based approach allows systems to adapt dynamically to change in conditions, disturbances, or external inputs. Whether used in simple systems like thermostats or complex ones, like industrial manufacturing lines, controllers ensure that operators are not only efficient and accurate, but also stable and safe. Now, their ability to maintain optimal performances with minimal human intervention makes them indispensable in both everyday life and advanced engineering. As industries and technology evolve, such as in smart manufacturing and robots, the role of controllers is becoming even more critical. They are now integrated with digital systems, sensors, artificial intelligence to create smarter, more responsive control systems. Controllers contribute to energy-saving, product quality, systems reliability, and overall process efficiency. In essence, they are not just tools for maintaining performance. They are key enablers of innovation and progress in automation and control. The continued development and fine-tuning of these controllers will play a major role in shaping the future of intelligent systems across every sector in the world. Now, these are the references. You can go to any of these websites to view more details about controllers. They do go in depth, and I would like to take a moment to thank every single one of y'all for watching this video, and I hope it helped out. If you enjoyed it, like and subscribe. Thank you.